We're live.
Hi, everybody. Welcome back to the Astro Imaging channel. This is Alex, and we're joined tonight by Tolga and Eric and Terry. And of course, Greg Crinklaw is here, and he's going to be telling us about SkyTools 4. Before we go too far,
Hi, everybody. Welcome back to the
oops,
Astro
it looks like
Imaging
I've got
This is Alex. And joined
I've
tonight
got
by
some feedback
Tolga
coming in on
and
me.
Terry. And of course, we're live.
There we go.
Hi, everybody. Welcome back to the Astro Imaging.
I've got too many screens running tonight because I'm trying to do something special for you. I'm going to take you over to YouTube for a minute. I want to show you some stuff over there. But before we do that, I'm going to take you over to the Astro Imaging channel. As you know, this is where you usually find us, and you click on that link and you will see us. And if you click on this link down over here, I am sharing my screen, right, Tolga?
Not right now.
Not yet? Okay, let me make sure I started my screen sharing. Okay.
You are now.
Okay, good. Thank you. That's because I'm sharing my screen. I want to take you to a different part of my program here. This is not working. Okay, this is us sharing the screen, and that infinite recursion is because I'm sharing my own screen and then showing you my screen. Over here, you can make all your comments on YouTube. See, Linda said a couple of things here, and the Astro Imaging channel, and Eric has invited you all to make your comments over here. We strongly encourage you to make your comments over here because as you do that, they will remain part of the video in the course of the for the history. So all your questions, as we answer them over here, they'll be over here. All your discussions, all your contributions will be here. But there are several other important things here. And if I can get down to the bottom of the screen, you'll see that there's a big subscribe button here. And may I suggest that you all, at some point or another, if you haven't, and I know 7,756 or something of you have already done that, want to subscribe to this channel, okay, and you sign in and you go ahead and subscribe to this channel. We need the subscribers because at certain levels of subscription, we can get more services from YouTube, and it enables us to reach more people with more tools that are more effective for everything that we want to try to do. So if you have not yet subscribed, go ahead and sign in and subscribe to this channel. Now, also here, you'll find a couple of other things, which I'm not seeing right now. You can sign into chat. I'm signed in as the Astro Imaging channel right now. And so there's some other things you can do over here, including contribute some money to the program. We're not asking you to do that. We don't want to be like NPR, National Public Radio, and have subscription pledge and that kind of stuff. So let me get out of here, but I remind you all to head into this so that you can keep your comments and subscribe for us. Okay. Now coming back over here, sharing my own screen. Let me see. Okay. I'm going to stop screen sharing and we're going to get on with Greg. Next week, I should tell you that Ann Zabladoff will be here, and she's going to be telling us about how we can participate in science programs by finding extragalactic objects and things like that. I've communicated a couple of times with Ann, and everything looks good. We'll be here next week. Now we're ready to take over for Greg. He's going to tell us about SkyTools 4. And you've been delayed several times by various things. And he's kind of groggy headed because he's been up doing what he should be doing. He's been out observing because it's a new moon weekend. And by the way, I've had the same problem because I've been at nightfall for the last 3 nights. And so I'm a little disjointed here. But Greg, you about ready?
I'm ready.
Okay, take it over.
Hi, I'm Greg. I'm the developer of SkyTools, and I completely lost my train of thought. SkyTools is actually two products these days. There's SkyTools 4 is one for imaging and one for visual observing, and obviously I'm going to be talking about the one for imaging tonight. Let me start my presentation here. I'm coming to you from Cloudcroft, New Mexico, which is just a few miles away from New Mexico skies. Here we go. There. SkyTools 4 imaging is very different from any other software you've ever seen or used. And it's important to understand that it's different in two main ways. One is it can calculate things that other software can't calculate. And two, it has an interface that's very, very different from anything you've seen before. So I'm going to give you an idea of both of those things, the calculations it can make, the interface, and why that's so useful, especially the two together. But the main idea is to improve your imaging at the front end. We all know that doing your image processing is really important. It's critical to, if you're making pretty pictures at least, to understand your software that you're using and to have good software to make good images. What SkyTools does is it's on the completely other end of that. It's to help you get good raw images in the first place so you'll have better material to make your images from. So the first thing I'm going to do is I'm going to talk a little bit about how it works. And this is the energy spectral distribution of a sun-like star. And the area under the curve there is the energy that the signal that we are capturing on our instrument. But this is what it looks like out in space. That signal traveled hundreds of millions of light years, possibly even more, basically untouched. Maybe a little dust has affected it and so forth, and then it hits the top of the atmosphere. And when it hits the top of the atmosphere sort of puts a fingerprint on it and changes it. It alters that spectral energy distribution. So if I want to model the amount of signal that we can get on your detector so that you can then know ahead of time what your image is going to look like, or at least the quality of your image, which is what we want to do here, then we have to take this all the way through from the signal out in space to the signal on your detector. So the first thing that happens to it is it goes through the atmosphere. And I should also say that this is a sun-like star. This is what the energy spectral distribution looks like for a mission line object, say a planetary nebula or a H2 region. You can see that now it's in the form of bright, narrow lines, which we can isolate with filters like an O3 line or so forth. So as the light passes through the atmosphere, some of it's scattered away, some of it's absorbed, and that affects different colors of light differently. And so when I say that it puts a fingerprint on the light, I mean that it's adjusting how bright it is in the red versus the blue or the green or the yellow. Then it hits your telescope optics. And that also leaves a fingerprint. Bounces off the primary mirror. Primary mirrors don't reflect evenly all the way across the spectrum. Neither does your secondary mirror if this is a reflecting telescope. Neither does a lens pass the light perfectly across the whole spectrum. So now we've got another fingerprint that's been added. Then we add a filter. And this is a narrowband filter for an O3 line. So now what this filter is doing is it's throwing out everything on either side of the O3 line and just keeping the light right around that O3 line. So here's one more fingerprint. Then we get to the detector. A lot of people are familiar with this. They look at what the quantum efficiency of the detector is versus wavelength, and which is what this graph is showing. But you have to take into account all those other things. There's the atmosphere, the optics of the telescope, um, things like the window on your camera. People tend to forget about that. Most cameras have a window, and those windows don't transmit light evenly across the spectrum. So you can see here on this particular detector, over on the left side is the blue side. It's passing a lot more light than it is over on the red side. So finally, we get an image, and in this case, just a bunch of stars. Um, the star, the light from the star is spread into a point spread function, which sort of makes a blob on the image, and the total amount of light that made it through from all the colors to the detector appears as in that blob. And it's spread out mostly by the optics in the telescope and by the seeing, the steadiness of the atmosphere, which changes depending on how high in the sky you're looking, um, or how low you are. So, and with just the seeing on that given night. We can predict all that if we have an idea of what the weather conditions are, what the seeing is like. We can predict what the peak at the center of these star blobs is going to be. And that's going to determine how faint we can detect a star. So what's the faintest star in this image? With SkyTools 4, if we run the numbers all the way through our imaging system, we can predict what's the faintest star we can find. We can also predict or detect. We can also predict which stars are going to, um, here's that being up all night part. I'm forgetting words. Which stars are going to be too bright for the detector? And which stars are going to be nonlinear if you're doing photometry? We can predict that based on your exposure time and the conditions at the time of the image. But the other thing we need to do is we need to model the sky background. So on an image, there's a sky background that comes from the natural sky, which depends on things like the altitude of the sun, or how far it is below the horizon, how far the moon is below or above the horizon, how far away the moon is, the phase of the moon, um, weather conditions, light pollution nearby. All those things can be factored in. We can make a model of the brightness of the background sky. The reason we do that is because the background sky adds noise. So what we want to do is we want to subtract that background sky, and it goes away in our final image for the most part, but it added noise. And we can also calculate the amount of noise we get just from the normal operation of the camera. So now we can compute the signal in any one of these stars on the image, and we can compute the noise, and then we can compute the ratio, the signal to noise ratio. And that tells us if we're doing something like photometry, if we're doing science, it tells us the quality of the data we're getting. We can also do this for extended objects, for a galaxy, for instance. I have a model that can tell you the brightness of the center part of the galaxy, the brightness of the mean brightness of the spiral arms, the brightness of the outer halo of the galaxy, and so forth. So you can pick a part of that and you can say, tell me how much signal I'm going to get. And more importantly, what is the signal to noise ratio? And when you do that, you get an idea of how good it's going to look. So let's say you're just doing you want to get a good image of the spiral arms of a galaxy. If you've got a low signal to noise ratio, it's going to look grainy. And we're going to get to that in a minute. So that's the basic idea. The basic idea is to use that model to predict the quality of the image that we're going to get. And that includes stacking a bunch of images on a single night or multiple nights. That includes different filters and so forth. So this all had to be tested. This software wouldn't exist if it wasn't for itelescope.net, because it allowed me to test over a wide range of telescopes and 20 some telescopes. So I could put in all the parameters for a telescope, the camera, and I could take some images and compare that to what the model predicted. How much signal do I get? What's the signal to noise ratio for both stars and extended objects? And in some cases, it worked great. And in other cases, it broke terribly. And you can see a bunch of telescopes here. I don't know if you can see my mouse cursor or not, but for this telescope, it worked great. For these two over here, it worked great. For this one, it failed. This one, it failed. This one, it failed. And the difference is the model worked perfectly for refractors, but it failed terribly for reflectors. And it wasn't just an even amount, it failed differently for each reflector. And I spent months trying to figure out why until I made this graph and looked into it more deeply. And what I found out was that the reflected light off of a telescope with commercial optics dropped off fairly quickly with how long it's been since it was last cleaned. Also, with how long it's been since it was illuminized. But I don't have enough data to really untangle the two. What happened is somebody actually studied this at Magdalena Ridge Observatory, MRO, which is here in New Mexico. And what they did is they did this brilliant experiment where they created these little domes and they put them outside of their at their observatory, and they hooked them up to sensors for the sky so that they would automatically open and expose a mirror to the night sky when it was clear. So these things would open and close, and then they'd go and they measure the reflectance. And this line here is their model for the loss of light of a mirror due to dirt. And you can see that this telescope here is actually a refractor, so it wasn't affected. This was a fairly new telescope; it was only about a year old at the time, and you can see it was 95% of the light was actually being detected. But as you got older and older, if you got 5 years, for instance, which is a long time to go without cleaning your mirror, you're getting down to 55, 60% of the light. So this is a dominant factor. This is really important. If you're trying to model how much signal you're going to get out on your detector, you have to take this into account. So thankfully, they developed a model, that's the line here, that I use in the software. So you have to, if you're using a reflecting telescope, you have to tell it the last time you cleaned the mirror. And if you clean the mirror again, you have to reset that number just in order to be able to do the calculations. Excuse me, I need to cough. So that's how we do the calculations. Let's talk a little bit about the signal to noise ratio. Image on the left is a single exposure. I think it was a 5-minute exposure of M81. And you can see in the spiral arms out here, it's all speckled. And that's because you're seeing all that noise. It makes it look bad. The middle image is 2 images stacked together. And you can see that's cut down on the speckling, which makes it a little bit easier to see more of the dark features in the disk. And then on the right, that's a similarly processed stack of 10 images. So that gives you an idea of what can happen to the signal to noise ratio just by stacking, which the software also models. So if you go out and you do 10 5-minute images and stack those all together, the idea is that SkyTools should be able to predict the signal to noise ratio. And basically, here's some basic numbers down here, just general, that if you're trying to just detect something, usually you need a signal to noise ratio of 7. Let's say you want to detect an asteroid, you probably want to get near that. 30 for pretty good picture quality. 60 will give you a very nice picture, speaking of which. So here's an example of a very nice photographic image. once you can use this model, or once you have this model and you can predict what you're going to get, you can use it to select appropriate targets for your imaging system, because every imaging system is different and every target is different. And because of all that fingerprinting that goes through the whole process of the light being detected, not every object is going to be easy to image at a high signal to noise ratio in a specific telescope. And a different telescope might be able to do a better job. So what we can do is we can compare different telescopes, and more importantly, we can use this to select target objects that are appropriate for your telescope. So that's the first thing that we can do with this model, is we can select target objects that are appropriate for your telescope. And this might be a good place to stop if anybody has any questions.
There's no questions over on YouTube. I have a couple, but let's wait till you get a little further on, because I think you're going to answer them.
Okay. All right. So moving on here. So the other thing I said that SkyTools is different about is the interface. And let me step back just a little bit for what we're trying to do here. We really want to plan to get the most out of our original observations, and that includes selecting appropriate targets for our imaging system and ones that we know we can get what we want out of it. And it also means imaging them at the right time of night, under selecting the best sub-exposure times and the best filter order, so that you optimize that signal to noise ratio. That's the game we're trying to play here. So the way the interface works is you start with the target selection tool, and I'll show you that in a little bit, quickly how it works. And then once you select a target object that is suitable for your imaging system, then you set up what's called an imaging project. That imaging project defines everything about your project. It could be you've rotated the auto guider around so that it's at a guide star. It could be that you've moved the field of view off to one side so that you want to get a nearby galaxy into it. And it also means your exposure goals. So what kind of signal to noise ratio do you want in each of your filters? If you're doing LRGB imaging, do you want to maybe use 2 times binning for the RGB filters and 1 time for the luminance? Since SkyTools can do that calculation, it can tell you what the difference in exposure times to reach the same signal to noise ratio are going to be. Once you've done that, you've got your imaging project, maybe a bunch of imaging projects. Then you move on to the scheduler. And the scheduler, you pick a specific night, and you have your list of imaging projects that you're working on. And you can just go ahead, and I'll show you this later on. You can just go ahead and say, schedule them all. And it'll make a schedule for the whole night. Or you can schedule them one at a time the way you want to, so you can sort of take control of how it works. And then once you've made your observations, you can point your project at the actual images. If they're FITS images, you can read the header. And it can then look at what you've done. You will add some sort of a quality. You can say, well, this was a really good image, this was a poor image. And it will look through those images and calculate the signal to noise ratio that it thinks you've achieved, given the conditions for each of those images. And then once in a given filter that you've reached the signal to noise ratio that you're trying to achieve as your goal, if you've reached that, it will stop scheduling it. And once you've done that in all of your filters, assuming you're doing more than one, it'll stop scheduling the entire project, and the project will be finished. And so you can use that to track your progress as you go, but then when it's done, you can archive all of your images. So now you've got somewhere you can go and you can say, where did I get those M13 images? What nights were they? How good were they? What was the weather like? that sort of thing. So that's the basic interface. So that allows you to do some things I did with an eye telescope. I wanted to see, using SkyTools 4 to plan it, I wanted to see what's the least amount of exposure time I could use on this particular telescope. I don't remember which one it was. In order to get a good looking image. And in particular, I wanted the stars to look good. So what this is 1 5-minute exposure in the R filter, the red filter, and 1 10-minute exposure in the blue filter. And SkyTools told me if I combined those two, the stars would be about the same size, and so they would combine in color very nicely. And I just faked the green as being halfway between, the signal as being halfway between the red and the blue, and got this image. So it's an example of the kind of thing you can do by planning ahead using SkyTools, because I could have just tried this to see what happened, but I wouldn't have known to double the exposure time in the blue filter unless I had a lot of experience with this particular telescope. So that's what the basic idea. And now what I want to do is switch over to actually bring the software up on the screen. And I'm not, it may actually be pretty blurry. And just give you an idea of how it works. And if you can't see it clearly, I can tell you what I'm doing. But this is another good place to stop for questions. So do we have any questions?
There was one question which you're probably going to get to. Someone asked, can you set it to perhaps take some extra shots just in case, to exceed your SNR, just in case you have some bad frames in there? Or does it evaluate it as you go?
It generally evaluates it as you go. But you have a lot of flexibility as you're going along. You can also, there's another mode, you can switch it over into another mode and not do it by a target signal to noise ratio. You can just say, on tonight, I've already figured this out using the software. It's going to want to do 5-minute exposures in this filter, and it's going to want to do 8 of them. I'm just going to tell it to do 10 and not worry about targeting a signal to noise ratio. So you can do that as well, depending on the project. But yeah, that's a good question. It's something I should probably think about. Padding things in case you get some bad images. Any other questions?
No, we're all set. This question came from the broke astronomer. I usually mention the name, so I'm not sure who the broke astronomer is. But.
Aren't we all broke? So this is the target selection tool, and I have it set up for the mythical Mesa Redonda Observatory here in New Mexico, and I'm using a TPO. I don't remember what camera was on here, but anyways, the basic idea, I've got it set up for tonight. It's new moon, and I've got a list of objects. This tool works off a list of objects. You can get lists from all sorts of places. We have a bunch of them on the website that you can download from within the software. You can make your own list. There's tools to create lists. You can add objects with called the database power search, so you can have it look for objects that are best for your telescope or your imaging system. Anyway, so once you have a list of potential objects, and this is the ARP galaxy list here, the idea is to narrow it down to just the good ones. So what I've done over here is I've decided I want to achieve a target signal to noise ratio of 30. So it'll be a pretty good looking image. And I want the maximum air mass for my objects to be 1.5. So that means that's going to keep them pretty high in the sky. And then I'm going to enable a filter here that's going to work off of those two numbers. And what that's done is it's added the constraint that we have to be able to reach this signal to noise ratio of 30 in 60 minutes or less, and that the object be above 1.5 air mass for at least 2 hours. And that's on any night of the year. So we're not working on a specific night at this point. And what that did is that narrowed down from the 339 objects we started with to 108. So this is your list of objects that are good, our catalog objects that are good for your imaging system or this imaging system. Next thing I'm going to do is I'm going to filter for this specific night, and that's over here. And this filter here is the imaging quality. And what this does is it's graded A, B, C, D. It's a measure of, let me select one here. Here's M32. This bar up here, this graphic up here tells us a lot about the current night. The gold line is the altitude of the sun. The background is shaded using our sky brightness model. The teal line is the altitude of the moon. You can see they're close to each other because it's new. The red line is the altitude of our target object, M32. And then there's a blue line here that may be hard to see. And that is the relative imaging quality throughout the night. And so what the software does is it calculates from this location, what is the best quality image I can get in, say, a 5-minute exposure. And then it says, well, it calculates that same signal, and that's based on signal to noise ratio. It calculates that same signal to noise ratio here when the sun is up, and it says, I can't get a good signal to noise ratio at all. So it puts the line way down at the bottom. As twilight comes along, it starts to rise. And then when it's very, very high in the sky, that is when we get the maximum signal to noise ratio. So what this is doing is it's telling us we want to image when it's high in the sky up in here. And it uses that information to assign an IQ grade. And I already selected just the A ones. So let's see what one that's, say, a D looks like. Here's an IQ grade of a D. It's poor. This object is setting right after twilight. It's not high in the sky, so obviously it's not going to have a very high quality. So that's one we want to not observe on that night. So I said just pick the ones that have an IQ of A during that night, so that we're just looking at the really good ones for tonight, at least relatively. It's a good time. It's a good night to observe each of these objects. The other thing I did is I said it had to be observable for at least 2 hours during the night. That's another filter I put on there. And that narrowed it down to 46 objects out of our original 339. And the last thing I'm going to do is I'm going to add a scale filter. And we've got a graded scale system here. A just means that, well, basically a poor grade means that it's so small that we're not going to really get a good image of it. It's maybe 10 pixels across. We want it to cover more of our image. So when it covers more of the image, that's going to be a higher scale. It's going to be a scale of an A if it covers the image fairly well. And let's look at this. So I'm going to pick this one here. I'm going to open the chart. This is the interactive atlas. It's just like any other planetarium program. I've pre-downloaded a digital sky survey image in the background so we can see what it looks like. And I'm going to open the camera window here. So this is a simulated view for an exposure, 5-minute exposure tonight using that telescope and camera. And I've also superimposed on that the digital sky survey image. And this is fitting the entire image in there. I can go to 100% scale. And this is what it's going to look like if you look at the image blown all the way up. And that's in the luminance filter. I can select other filters and so forth. What was I doing there? I was just showing how you do that. And you can see that it covered a fair amount of the image. It covered enough pixels. And in fact, right here, it tells us 653 by 351 pixels was enough to get it a scale rating of A. And we can lower that to a scale rating of B if we want to. And it's included some that are smaller. So that's how that works. We're just going to go with the A's here. So we've really narrowed this down for this particular night. These are our best objects. So I'm going to pick one. I'm going to pick the one we just looked at, and I'm going to create an imaging project for it. And this was the next phase. The idea is to do this for a bunch of targets. and then you build a list of imaging projects, and then you're going to schedule those imaging projects later on. This stuff here, most of this stuff doesn't apply. It's specific purpose stuff. I'm going to assign this to an imaging program that's just a bookkeeping thing. So what I can do here, this is where we decide the composition. Let's say I want it to sit there, and I'm going to rotate this around. This is my guider window, so that this star here is in the guider. The software knows which stars are good for your guide scope. In this case, it's the green ones here. So this is one that the auto guider will like. So this is a good composition. Maybe move it over here just a bit. And when we go to schedule our observations, this is the image that we're going to get right here. The next thing is exposure goals. I'm going to select some filters. Let's go with an LRGB. There we go. And we're going to go for a signal to noise ratio of 30. That's what we were looking at earlier. And we're going to target that signal to noise ratio for the arms, or if it's, excuse me, if it's not a spiral galaxy, then the main part of the galaxy, not just the central bulge. So that's what the signal to noise ratio is going to refer to, in this case, the spiral arms. So this tells us how much total exposure time is going to be needed in each of the filters. You can see the luminance, it's going to be 2.3 hours to reach our signal to noise ratio of 30. And this is just on a generic night. But you can see for this red filter, it's going to take a long time. So what I'm going to do is I'm going to customize that to use 2 times binning. And you can see that really drop down the amount of time we were going to need. And I'm going to do that for each of the RGB filters. So now we've got a more doable project with the luminance is going to be the longest. It's going to require 2.3 hours of total imaging time, but the other filters are now 96 minutes, 104 minutes, and 108 minutes. So now we're done. We click done. So what we've done is we've set up an imaging project. We move on to the next part, which is the scheduler. Excuse me.
Greg, do you have time for a couple of questions?
Absolutely.
Where do you get the list of targets? Is this a list that you've compiled yourself, or can you select among NGC objects, LDNs?
I know I was speaking quickly, but there's a lot of ways to get these lists. You can download them from our website. So you can come here. There's just a bunch of pre-made lists. You can read them from a text file. If you've got a file with a list of objects in it, that's all it will need by name, designation, or whatever. It can create a list from that. You can share lists from one person to another using a SkyTools file format. And once we have a list, we can add objects to it. I can just type in a designation here and add an object from the catalog. And SkyTools has a huge database of objects, by the way. Or there's this complicated tool here, or powerful tool here, where you can go through and, using a variety of different filters, create your own list suitable for your imaging system, and if you want it to be, or good objects from your location. There's all sorts of filters you can put on this. You can even just look at a specific constellation to create your own list.
Okay, there were a couple questions about using a CMOS sensor.
Yeah. It does the calculations for the CMOS as well. So it's not just for CCDs.
And another question about if you have variable length of exposures, what do you do about your darks?
Well, that's up to you. You can, let me show you, set up this imaging system here. So there's a lot of things you set up for your imaging system. Kind of mount you're using, the type of control system you're using. And I'm going to speak about that in a minute too. One of the things you can do is you can set up the exposure times that are allowed. And this one, it just says the exposures have to be 1 minute or longer, or up to 10 minutes. But what you can also do is enter a list of allowed exposures. And this is something we often do with eye telescopes because they do their darks at specific exposure times. So what you could do here is you can enter a list. You can say, I'm going to allow 60 seconds and maybe 300 seconds, and that's it. And once this list is entered, it will always recommend the most appropriate sub-exposure time from that list. So it'll either be 60 seconds or 300 seconds.
Greg, could I interrupt here for a second?
Yes.
Perhaps the concept that we need different exposure times and therefore different dark times comes from what I think might be a misunderstanding in what you said. In order to reach 30%, you need 108 minutes of red and 92 of whatever blue.
Right. That's total.
That's total exposure
It's
time,
total.
not the sub-exposure time.
Not the sub-exposure.
Okay, so you could reach that 108 minutes by doing 11 10-minute exposures.
Oh, absolutely. And we were about to see how that worked.
Okay, so so the question about the different exposure times, that's not an issue.
That's total. That's what we want. Yeah, that could be done over multiple nighs. And depending on the conditions of the night, SkyTools might recommend different sub-exposures. But it'll all add up. When you combine it all together, it'll add up to the signal-to-noise ratio that you're aiming for.
Greg, I have a question.
Sure.
You talked about sky background.
Mhm.
How do you measure that? Do you have a procedure that's doing the setup process?
It's calculated by the model. And right now you put in the amount of light pollution you have at the zenith, which you could measure and put that in. Or you can just estimate it from, in fact, SkyTools has a light pollution model. It can fairly accurately tell you what the sky brightness is going to be at the zenith for your location.
Okay.
And then it just factors in all the other things, the things that change, like the moon.
Sure.
But down the road, I'm going to add a tool where you can tweak that with your own images, and you'll say, okay, here's an image I took, and you can read the background off of it, and then SkyTools will say, okay, well, that's the background you got, and you're pointing in this part of the sky, and then maybe you moved it to another part of the sky, and it will eventually build a model of the sky brightness depending on the part of the sky you're looking at. Right now, it assumes there's no sky dome. I mean, not sky dome, but light dome from a nearby city. That's a complication that it can't quite handle yet. It's assuming you're at least down to 2 air mass or so. It's assuming that the sky isn't brighter in one direction than the other.
Greg, I have one more question before you continue.
Sure.
So the seeing varies by the altitude of your target as it's perspective at night. And seeing varies for other reasons too, almost every night.
Yes.
Can you account for seeing as it changes? So it starts out at 1.5 and then goes to 1.25.
Absolutely.
What do you do?
Let's move on to the scheduler here. So what we did in the target selection tools, we were looking at just generalities. On a typical night, on typical conditions, these are going to be good objects. And in fact, I did actually set it up for a particular night here, didn't I? Okay. So what I can do is I can enter the seeing here, and wow, okay. Without fail. I can use this thing for a month by myself, and I can show it to somebody and it'll break every single time. And it's broken hard. Hold on. Well, that's embarrassing. Yeah, it's very unhappy. Hold on a second here. I apologize for that. I am actually known for developing software that is stable. So I just undermined that whole thing there.
Hey, by the way, did you notice you got 2 planetary nebulas in that image?
Yes. Yeah. In fact, I
Little one.
composed it so that I could do that. Yes. There's the little one right there. Yep. Okay. So we're back to the scheduler here. And, well, actually, we were looking at the target selection and I was changing the weather. And I have no idea why it broke. I hope I didn't just break it again by switching back. Okay. So you can vary the seeing, but at this point, all we're doing is we're ahead of time. We're maybe a week in advance, a month in advance. So we're just sort of estimating what the weather's going to be like to pick our targets. But when we move on to the scheduler, now we're setting it up for a specific night. There's an auto selection here for the weather. This is where we do the weather here. And what that does is you set the typical weather on a monthly basis for a whole year. And that way, when the software is planning ahead, it can use some value that's going to be different in January than it is in June, right? But for a specific night, we usually want to use what we think it's going to be. And we can change that as we go, depending on what kind of imaging we're doing. Because when we get to the next phase of this, we're going to find that it branches out into a large number of ways to observe once you've created a schedule. So I've set it for fairly good seeing, and that's actually changed all the calculations here, and it will change the schedule that it produces. If I click the auto schedule button, it's just going to take all of these projects. Each of these is a project that's been defined, and it's going to figure out the best order to image them in. And in some cases, it's going to do the whole project. In other cases, it's just going to do one filter and so forth, depending on the conditions on that night. But I can also just pick one and say, let's schedule that one. And it has scheduled it for 1921. And it's going to do 7 10-minute exposures at 2 times binning. I forgot what object we were actually doing. That might have been it. Then there's a meridian flip in there because this is a gem mount, and then it's going to get the green filter. One of the other things you do to make this scheduler work is when you're setting up your telescope, you put in estimates of how long it takes for things to happen. What's your actual slew rate, not the one from the factory, but what does it usually work out to be? How long it takes to change filters, all that stuff, so that it can sort of estimate what the automation is going to do. And in this case, this particular telescope is, it uses ACP to plan. And iTelescopes do the same thing. So once I've created a plan, and I can put as many targets in here as I want, but I'm just going to go with the one, I can save it. And it has produced a plan for imaging just that particular object, which you can then upload via ACP, and ACP will make the actual observation. So SkyTools is sort of the brains of the outfit, and then ACP, or whatever your control system is, will actually go and do it for the most part, at least at this point in time. So what it's doing here is 72 60-second images, that was for this. Yeah, that was for the green filter. You can see it's chosen wildly different things depending on the filter. And the luminance, it's doing 7 10-minute exposures. And in the red, it was doing 16 at 540 seconds. And that's just based on the model and what it thinks is going on that night, or what you've told it about what's going on, including what you think the seeing is going to be. And you can update that as you go on for the night. By the way, these color bars down here, the green is the period of the night that you want to really image this object. And down here, this tells us what's going on with the schedule. This is the initial slew. These are things like filter changes and focusing and stuff like that. And then this is an observation of a filter, another filter, another filter. So that's one way you can use this. You can use it with ACP, which works really well. And the itelescope.net, if you're familiar with that, where you can just rent time on telescopes around the world, it uses these ACP plans, so you can upload those to all of their telescopes and just schedule, say, an hour at the right time of the night, upload your plan for that hour, and I can just tell it that I want to make a schedule from 2100 to 2200, and it'll make a schedule for just that time block. Another thing you can do is if you've got ACP Expert, what ACP Expert does is it figures out when to observe each of your objects. You put a bunch of objects into it, and it figures out right now it's dark. What should I be imaging? And in order to make those decisions, it uses what are called constraints, which you have to program into ACP, ACP scheduler. You have to tell it what you think the constraints are for each object. And it turns out each object, it's complicated. It turns out each object can have different constraints. So again, what SkyTools does is its role is it will figure out the best constraints, pass those on, it will upload them straight to ACP Expert, and then ACP Expert runs completely unattended. It will just go off and do its thing. Images will be obtained, and then you click query status, and it will tell you, I'm not hooked up, so I'm not going to do that. It will tell you all the images that were obtained, and it will then automatically figure it out what has been observed and what hasn't, based on ACP Expert. So that's a very, very powerful way to do your imaging completely unattended. This might be a good place to stop for any questions. Excuse me. No questions?
I don't see anything over on YouTube. I have a general question.
Sure.
Since you've done some research, is there a better time of night to use the red, green, or blue filter?
Yes. Yes.
Can you tell me what that is?
The software can.
No,
Because
but
it's complicated.
it's better to do the green filters early and the red filters in the middle.
Well, see, that's the whole point. Is people, I can give you a rule of thumb, but it's not going to apply for every situation and every night and every imaging system. It's your imaging system is different from somebody else's. So if they tell you that my rule of thumb is I always start with the red filter, they're probably mostly right, but not always. If there's a little bit of moon up or your conditions are different, your imaging system is different, it's going to affect that choice. So that's the point of the software, is then because it knows a lot more than you do about what you're going to get out of this in the end, it can go ahead and say, well, what if we started with the red filter? What if we started with the blue filter? And then it does the calculations and then figures out for you that you really want to start with the red filter. Hope that answers the question.
There's another question that came up from Ross. What do you do for high dynamic range targets where you have to take long and short exposures, like Orion?
Right. So back when we were creating our imaging project, I decided I wanted to image, I wanted to calculate my signal to noise ratio for the disk of the galaxy, for the spiral arms. What I would do in that situation is I would create two separate imaging projects, one for the bright part and one for the fainter part, because every type of object is going to have that kind of a choice. For the Orion Nebula, it's going to say, I want to do all my calculations for the bright parts, or I can do all my calculations for the faint parts, or I can do all my calculations for the really, really super faint parts. And you could make that 3 different imaging projects if you wanted to. And it would treat them separately, and then you would go ahead and put them all together in the end. Other questions?
No, I think we're good for now. Okay,
so another thing you can do, and this is going from one end of the spectrum to the other, is instead of using ACP Expert or Scheduler, let's say you don't have an automated imaging system or an automated control system, and you're out there with your telescope all night taking your images, then in that case, you can connect to your telescope. And this tool is a sort of on the fly scheduler. And this is for this observatory at this time of night. And this line right here is telling us that it's 2030. And it's telling me over here that these are the objects that are available to image right now. I can schedule one. So now we've scheduled that one object, and it's chosen the filter orders and which filters to do and which filters to get another time. All that stuff happened in a flash there. Then I click start imaging, and the telescope starts to slew. And once it gets there, you're sort of the automation system. Depending on how you do it, you've got your camera control software. It will tell you to start with the luminance filter. And over here, it tells you, okay, all right, we set it to the luminance filter. So I went and I set up the luminance filter, and now it's telling me what my exposure should be. So binning time 2, 10-minute exposure. The camera angle should be at 69 degrees. In this case, it's a rotatable camera. And then you start the exposure, you click the button, and when it's done, exposure's over, you click it, you log the observation, you tell it what you did. It's actually, in this case, is a series of exposures. And then it'll tell you to change the filter and move on. So this is yet another mode you could image in using your own camera control. And at this point,
Greg, while
yes,
we're here, this is saying that, well, for instance, the blue you've got highlighted right now says change filter to green, and that will take 5.0 minutes.
Yeah. This isn't a real imaging system, so
Okay.
I just put in random numbers. And in testing, I like to put in long numbers,
Okay.
so I can see what the software is doing. This is a test
But-
imaging system.
But your SkyTools for imaging software does not actually change the filter.
No,
It
not
just-
in this particular case. No.
Or is there another case in which it would?
Well, you could. That's coming in the future. I was just going to address that. So obviously, you've gotten to this point. That what SkyTools does and does best is help you plan your imaging system session.
Okay.
So
if I were
what
using Nina
okay.
or Sequence Generator Pro or something, I would actually tell it at 2025-39,
Right.
I want you to go start the sequence.
Yes.
And,
Yes.
And then we're going to start with some luminance, do your focusing, and then give me 6-10-minute
Yes.
binning to, etc. And then go to green, and I
Right.
actually type that into my sequencer.
Yes.
However I put it in.
So this is SkyTools 4 because it was separated. All the imaging was separated out of the SkyTools software and put into a new product just for imaging. So in a lot of ways, this is SkyTools 1 for imaging. And so the next thing we want to do is once we've gotten the part where SkyTools is doing all the calculations and it's doing it in a useful way, you probably don't want to be putting the stuff by hand into SGP or Nina or whatever. So the next step for this software is to expand the possibilities for what it's connected to, including even adding camera control and plate solving on that stuff to the software down the road. That won't be any time. That won't be in the next year or two, but because I'm going to concentrate on being able to have the software talk to things like SGP, so that you don't have to do your own filter changes or whatever.
Yeah, in SGP, you can download target data and stuff like that. And what you're saying is, well, if you worked it right, maybe SGP will someday be able to download
Yes.
that whole line of
Yes.
stuff there.
And yes, that is exactly right. And I spoke to them at NAIC last year about doing that. The hard part is on their end, their software isn't really set up to accept that kind of information. And so it sounded like it was going to be a lot of work on their end. So it's going to be up to them really whether or not that goes forward. But I've looked at some of these others that I've only really just discovered, like Nina, in just the last couple of months. And interfacing with those looked like it'd be a lot simpler for SkyTools to do. So yeah, that is the idea though, is to take as much information as we can so that it becomes as automated as possible.
Okay, thank you.
Greg,
Yes.
could you use the Windows magnifying tool to just to show the audience the small print on the right, like that scheduler? On YouTube, it looks a little blurry, and I want them to see a little clearer.
I'm using a 2-monitor system here, and we tried the magnifying tool earlier, and it messed everything up to the point where I had to restart my presentation.
Oh, okay.
So
All right,
I can read you what it says. It says first thing is to slew to NGC 6217. It gives the position angle and how long it thinks that's going to take. And then it says to change the filter to luminance, how long it thinks that's going to take. And there's the numbers you put in for your system. And then it says 6 10-minute exposures at 2 times binning with a gain of 0 in the luminance. And then it tells you to change to the green. And then 32 1-minute exposures in the green. I'm not sure why it's chosen that.
I might be able to do something on my end over here. Let me see
Okay.
if it works.
Okay.
So Greg, right now the plate solving is a task of ACP or FTP or Nina or.
Yes. At this point, I wanted to get the core functionality of the software done before I started moving into and working. And there's still some polishing that needs to be done so that it works in all situations. It does what you need it to do in all situations before spreading out and having it actually talk to more than just ACP. I needed ACP because I was doing my testing on iTelescope, and it is a very sweet combination, ACP and SkyTools for imaging, because just the way the two work together, especially Expert, that's actually very powerful with ACP Expert.
And I assume you're going to get to the cost of the software here pretty soon.
Mm-hmm. It's $199 US. So cheap compared to some software, expensive compared to others. It all depends on what you want to compare it to. Let's see. So I'm actually getting near the end of my presentation here. Let's see if I've got anything else I want to cover. Let's see. I mean, we were just sort of talking about this. The future here is my last slide. Integration with other control systems. Maybe down the road, add direct camera control myself and the plate solving and all that, so that SkyTools itself can control your camera, filter wheel, rotator, dome control, all that kind of stuff. And just as an aside for people, if there's anyone out there who does electronically assisted observing, that doesn't fit this paradigm. That's not classic imaging. So that is actually folded into the visual project because that's actually done very similar to the process is very similar to visual observing. and I'll add a couple of things that this will work with the DSLR on a tripod. So there's a wide range of calculations possible here, depending on your imaging system. And I think, let's see, let's stop sharing. And so that's pretty much my presentation. And do we have any more questions?
So it's basically what this is doing is maximizing your time in the sky.
Yes.
You're shooting the target at the best possible. You're using the appropriate filter at the correct altitude.
Yep.
It's
and that
telling you,
becomes
you know what, you should be using hydrogen alpha filter X many degrees away from the moon, and
absolutely.
oxygen filter for
Absolutely.
this many degrees off the, so that this is maximizing your
Yes.
productivity
And
to
where that
reach your defined signal to noise ratio.
yes, and where that
It's an
becomes
excellent tool.
particularly useful is if you've got a whole bunch of projects you're doing, which ones should I be doing at the first part of the night, middle of the night, later on? I mean, let's face it, most people, when they're planning their imaging system, they just kind of go, well, I want to get it when it's high in the sky and and there's no moon. And what I'm saying is we can do better than that. Do you have any other questions?
Yeah. Eric, how are
I
we
think
doing?
we're all set,
There
Alex.
there was a
there?
question. Oh, go ahead, Eric.
No, we're all set. I don't see anything more over on YouTube.
You know, when your program broke there, hate to bring it up again, but
Yeah, you
particularly
had to remind me of that.
particularly now that we can see your face. The, how'd you fix it? Did you shut it down and bring it back up?
Yeah, I actually had to kill the process, which is very embarrassing.
That was very quickly fixed, though. It wasn't a long.
Yeah,
It
I
wasn't a
just,
long process to
it
go
was
out.
popping up an error over and over again for each object in the list, and that made it harder to stop. So I had to just kill the process. And that's the kind of error that really should never happen. So I'm going to be really curious. The first thing I'm going to do on Monday morning is, which I guess is tomorrow, is figure out what happened there. Because at the very least, that error should have been better handled.
Okay, well, let's
Yeah,
not
very
dwell on that.
embarrassing.
However, when you want to come back and test it, we'll give you time on the Astro Imaging channel so you can display it as it. Okay. Are there other questions?
Greg, I've got one question.
Aaron?
Sure.
Yeah.
Does it interact with the scheduler database on ACP? Will it adjust the plans?
Yes. I didn't really go into that deeply, but what it'll do is it will it submits objects to scheduler, and then you can query scheduler later on to get the information on what actually happened, what's actually been imaged, what did scheduler do, so that it can kind of keep track of everything for you.
So it'll dynamically change it as required.
Yes, and it's fully integrated with scheduler. It can talk to it both in and out.
Oh, thank you.
Okay, we're getting ready to wrap up here, guys. Eric and
I have one more question.
Sure.
How do you what do you do with update? Like, do you update it often? And if somebody has a question, like a technical question, do you have a forum or do you answer them
Yes.
by email? How does that work?
Both. I have a forum, and I answer by email, and I take pride in answering people at 3 a.m. on Sunday night. Sometimes, if I'm around, I just I think that's really important to fully support the software. So I do that, and I also fix bugs as quickly as I can and put out updates so that nobody bothers me anymore. That's my ultimate goal, is that nobody emails me because nothing ever breaks.
I've got one more question, Greg.
Sure.
Has it got a recalibration mechanism? Like if you wash your mirrors, you said the metrics do
Yeah.
change?
You go back in and you just change the date to the new date when the mirrors were washed, and it will update all of its calculations from then. But this is where it got actually really very complicated, because let's say you put a new filter in your system, changed one out. Well, you'd been using that old setup and you've created imaging projects for that, but now your imaging system has changed. SkyTools still goes back and looks at those archived observations and makes calculations on them. You don't want that to change. So it actually archives the telescope data at that time with your observations. And then from then on out, any imaging project that hasn't been finished, completed, is going to be updated with the new filter you put in. And that includes things like setting it, telling it that you've washed the mirrors.
And as your mirrors or other things change, the model is changing.
Yes, yes.
Okay.
And it doesn't forget what it was like back in the old days,
Okay.
which was actually pretty complicated to make happen, but
Excellent.
it's working.
Does it make any judgment as to how well you cleaned that mirror?
No, not at this time.
It's very, very complicated. Okay. If I invest 199 bucks in it and its current state of development, and in 2 years or so, well, first off, do I have a subscription fee for next year?
No, I don't do subscriptions.
And in 2 3 years from now, you figure out how to get it to interface to SGP or something else. What am I gonna? I'm gonna pay an upgrade fee, or what?
Yeah,
What, do you-
what I really want to do is do the opposite of what I've always done in the past, which is long periods of time went by, big updates, and then I charged half price. What I want to do is I want to aim at an update. This does not include bug fixes; those come out continuously, but an update with new features once a year, and then there will be a nominal fee for that. So it's sort of like it's kind of like a subscription, but it's completely voluntary. That nominal fee, somewhere between $25 and $40, something like that.
My old software will continue to do what it always has done.
Absolutely.
If I want the new features, I have to invest in 40 bucks.
Yeah.
Or something like that.
That's what I'm aiming at.
Okay.
Hey, Greg, someone asked about a Mac version.
I don't bother with a Mac version because the emulators work so well. It would take a lot of programming time for me to create a Mac version when we have a lot of Mac customers, and there's emulators that come with the OS these days that will work with SkyTools. So, or you can invest in buying one that's is a really nice emulator, which will just put SkyTools up on your Mac desktop like it's another Mac program. Excuse me. So it would take an enormous amount of my time to do something like that. I'd rather work on the astronomy.
Unless, is there more questions? Then I'm going to start wrapping it up for the Astroimaging channel. And I want to thank Greg for being here tonight and introducing us to something. Also for reminding us how sloppy most of us really are. Saying, I'm going to go red down here and then green, and then I'm going to go luminance up the top, and leaving it at that on whatever I'm going to image today. That's, I think, what most of us do. And I always am reminded of how much better an astroimager I could be if I actually paid attention to what I need to pay attention to, like the stuff Greg has told us about. I also want to remind you that next week, an amateur professional collaboration to discover gravitational wave sources. That's what Ann Zablutov is going to be talking about next week. We all know what gravitational waves are now. I had the pleasure of meeting a Nobel Prize winner who got his Nobel Prize for having helped discover them, and just a couple months ago. Anyway, he told us a lot about it. I'm sure Ann knows a lot about it too. She's going to tell us, and she is going to tell us how we, you and me, can participate in help finding these things. So if there's nothing else to say, Tolga, you want to take us out?
Good night, everybody.
Good night.
Thank you.